an approximation that I went about an hour ago I talked about.
So then for day 1 to day 2, the only thing that's changing is to see if it's converging upon a solution, but no other.
That's correct.
Okay.
With another little modification, if snow is falling, then the magnitude of the snowpack grows, because you have to predict that too.
Oh, okay.
So you've gone however many days was necessary to decide, okay, I'm ready to predict the solution for this particular season. And the next the next loop out is the latitudes loop. And I'm still having trouble understanding that, because why do we need to vary the latitude if we're interested in only a single spot on Mars?
You don't.
So what is that?
You can force it to just do one latitude.
Okay. So that would be used if you were solving for many different locations.
Right.
Okay.
And there's only a purely historic reason for this is I wanted to calculate the orbit geometry. Remember my philosophy, move everything out as far as you can to the outermost loop? Well, I can push the orbit geometry all the way out to the season loop. And I don't have to do all that messy solving Kepler's equations and so forth. But once per season, yeah.
So then my other question is, if we have 24 of the hours, that's just what, and then each hour has so many time steps in it, so 17 or whatever, which are necessary to converge upon the solution for that hour. And then the hour is just so that you are outputting that.
That's right.
And not every single one.
Right. The hour is simply how many times a day am I actually going to report to the outside world what the solution was.
So you don't have
thousands. And in fact, that reporting is only done on the last day. Don't even worry about it until we get to the last day. Randy.
I want to check too. She said something this morning, also reminded me of something I saw in the paper, that it's also on a per layer basis. So if you get a convergent solution for like 25 of those 30 layers, you only spin forward on maybe the last 5 layers as if you haven't converged on that yet, or you have to keep doing it for all the layers.
You keep doing it. You either there's a lot of convergence tests, but ultimately, as I said, there's one logical test. Have I satisfied that set of requirements that allow this to be the last day? That's a single flag that comes from all kinds of junk. Am I ready to try one last day?
So where does the double time step come from? You mentioned that on a layer.
Doubling. Time. That's pretty tricky. And I'm going to actually, seeing as Phil's raised the board here, I'm going to actually show you what this looks like. I don't need it. Okay. This is the surface. And here is layer 1. And here is layer 2, and so forth. And they get gradually thicker. And here is midnight. And every little circle means I actually did a calculation. Actually, a mistake. Open circles. Because I actually do the calculations at the layers, not the interfaces. But it turns out there's a lot of shenanigans. Any numerical scheme, you have to deal with boundaries and layers and blah, 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 blah. Okay. Down here, eventually we got some great big thing. You remember the convergence criterion has to do with delta t and delta t this way and delta depth this way. At some point, let's imagine I'm doing the calculations every this often, all the way up. I'm doing them every so often. I get down here and it turns out, hey, I'm really stable, so now I only do this set. I do every other set. And the next layer, I do every other time step.
Only for that layer?
For that layer. This tells you how often I do each layer. Because remember the loops go from top, layer 2 to k sub n, kn. I don't know if you remember that, but hang on, it's not very far back. Is this going to, wait a minute, why isn't it going back? Here we go. Wasn't it backwards? Maybe it was forwards. Who messed me up, Phil?
Or me.
Where's the statement about, there it is. 2 to Kn. Kn, this is the depth, right? This is an index. It's a vector of 384 integers. There's a different value in there for every time of day, or can be. And so Kn, I pre-compute at the very beginning when I start a case, way at the outside loop. I calculate what's this comb going to look like. How far do I have to go down each time step? And so forth. And this, the index in that direction, is Kn. And I allow up to 6 firm-coded time doublings. Once I get to 6, I figure it doesn't make any sense to, I'm now already 2 to the 6th sparse in my computations. Why go any farther? But that's you could make that any number you want. So this is it's like a comb. How deep do I go at each time step? And of course you have to change as for this layer, the equations have to change, because if you double the time step, you better double the amount of temperature change you have based on the heat fluxes. Did I answer that question? Okay, I guess you're now in charge.
So maybe I'm the only person in the room who's still a little struggling. But so here's the sun, and here's Mars, and you're saying there's, in a typical case, there's 40 seasons in a year.
I use 40, 80, 84, some significant
so
little.
Each one of these represents a season.
Yep.
And for Mars, that's about 16 days apart. Okay, so this is 16 days. Okay. Now, you start with an isothermal world, and you put the sun somewhere. And each time through, this guy will move over to here a little bit, and here and here.
Right.
But if you let it keep going, eventually it's going to, for the sun in a fixed position at 1 a.m.
Okay, that's not the way it works.
Okay, so you let it go through the whole day.
That's what I do, right.
Okay, so you converge in this direction.
Yep.
So
Yep.
now this guy's moved to here, and he's moved to here, but gee, these guys are still isothermal because they just haven't been around long enough.
Yeah, sort of.
Okay, so you'd go through 24 hours, and you'd end up out here with something that looked.
Okay, that's a midnight profile. Turns out it's midnight.
Okay, so this is right. So this is a midnight profile.
And now we haven't discussed it, but this is a potential weakness of the system. And the weakness is the temperatures at midnight are sort of not very dependent upon what happened during the day. And I'm doing all my tests at midnight. Shouldn't I be doing them at noon? But in fact, they're all done at midnight.
Okay, so let me keep going. So
Okay.
you end up with a midnight profile.
Day 1, midnight.
Day one, midnight.
Yep.
So it comes over to here. Okay. Now I put the sun back, and I do it all again.
Yep.
And I end up with a day 2, midnight.
Bingo.
Okay. And those are different.
Yep.
So I'm not converged yet, or I'm not stable, or whatever. So do it again. So typically, you're saying that after about 3 to 5 days.
I actually haven't mentioned that number.
Well,
all I've said is I don't.
Okay.
That's all right. It's all right.
After n days.
Everybody loves it when I catch you at something.
After n days, this thing is, in this case, it's unchanging, right? It truly is.
It should theoretically be
unchanging. Because the sun isn't moving.
Yes and no.
Once the temperature change is close enough to this asymptotic trend that you pre-calculated, you say, all right, we're done.
Actually, that's not quite right either.
That comes next.
I got to.
So for all of this, that Mars has not moved. Mars has stayed right.
Mars is spinning in place. That is correct.
So, but if I did this forever, eventually these are going to be completely unchanging.
Correct.
Okay, because nothing else could change.
Right.
Okay, so I get to some stable condition down here. And then, am I correct in saying then you move Mars one, you actually
No,
do
I don't.
physically do-
I don't. What I do is I just do this. When I get to where it's stable, I declare the next one will be the last day, and I do it again.
Okay, so at the end, so at that point, then you actually do compute the season. So this becomes the last day. When this thing is stable, it's not unchanging, but it's stable. It's
Right,
linear.
that's right.
You project ahead and you say, okay, fine, I'm going to do a last day. You're going to calculate the temperature.
Right, there's no projections are done until after last day has been declared and last day has been run.
Okay. So
Okay, and then you do a seasonal projection.
where did, I guess I'm lost.
Okay, here's why.
If you
Here's why.
manage to
Ideally,
allow-
I'd be doing this: day 1, day 2, day 3, day 4, day 5.
Right,
I don't. I do day 1, day 2, day 3, day 4, day 5, all at the
Right.
same place.
right.
I get out to day 5, and it looks like, okay, these things look like they're stable enough.
They're doing this. They're changing a little bit.
Yeah, they're
but not
changing in a
much.
predictable way
Right.
that I can now take at each layer.
So so the last
For
three-
each layer, I do an asymptotic prediction based on the last 3 midnights.
Okay, so
The
you,
midnight of last day, the midnight of last day minus 1, the midnight of last day minus 2,
okay, and so you project out this.
on a layer by layer basis.
So you project out that to what it would be 16 days from now.
That is correct.
Okay. And that then, this becomes the seasonal, this is what's reported.
That is
This is
that
the
goes
temperature.
that goes into that bin for that
that's
season.
the temperature at this bin.
That's right.
Then you physically move Mars here. Now you don't have to start isothermal.
I start
You
with
start with this,
that's correct.
and you do this process again. It's changing a small amount. It's linear. You say, fine, I'm going to project ahead 16 days. Okay.
That is correct. I'm glad you did this because it reveals, it's not easy.
What? Yeah,
To-
I haven't think
this
about
is
this
what
for
it
long
actually-
enough. I just wanted to.
Are there other questions about this? Should we all applaud Phil for volunteering to, thank you. Phil. Yes.
If you were to leave the sun basically in the sky forever, wouldn't it just keep heating up? Because at first you were.
Which one do you want?
No, because it's radiating away. I mean, it's going to get to some
That's-
stable point.
But I think
That
that
one,
would
sorry.
get way too hot.
Okay.
Remember, it is per hour, so the sun is moving, then eventually.
No, but you were saying that if the sun was not rotating, if you just held the sun at the 3 o'clock in the sky.
Oh, no, I didn't mean that. I
Okay.
mean, if you kept Mars in the
Okay.
same place and let it spin on a 24-hour day.
Yeah.
So that.
No,
so-
I understand. I thought that you were saying it the other way, and I was like, wait.
No, it would.
Okay, okay.
It would.
No, it's important to recognize that KRC declares a season to be Mars in a specific spot, and it spins with that aspect of the geometry. So you have a solar day, but every day is exactly the same at that season, unlike real Mars, where every day is incrementally different.
I think this was asked already, so
Yeah.
this wouldn't really work for Mercury, right? Because during a day it's going, 2
That is,
miles away.
yes. Mercury, you'd have to, I don't know, I hadn't thought about this. I'll bet you could do it. KRC could probably do it, but it wouldn't do it without some thought about the input parameters. It was not part of the design consideration, was a sidereal locked planet.
But if your days are small enough, you can approximate.
Yeah.
Probably could approximate.
I'm going to say at the moment, I could probably make this work for Mercury. I don't think anybody else could with the amount of information I've given you. But it wasn't designed for that, so you have to realize from the outset. The other thing to recognize here, and I've never really thought this through, is when Kim looks up a season, what is it she's looking up? She's looking up the extrapolated prediction based on a geometry some amount of time in the future. So there's, but this is the well, I'm going to say there's an analogy. This is the philosophical position you should always avoid. If you're doing a finite difference solution, it isn't fair to ask what goes on within a time step. It's simply not fair. And in a sense, that's what we're asking here. We've got a numerical solution, which I actually approximate seasons by these things. And it's sort of not even fair to ask what goes on inside here, as long as I've, somehow represented reality. But, and people get hung up on this. They start asking themselves, well, what actually goes on within a time step? And you got to have the right equation to start with, which I proclaim that I do. And then that's it. You can't ask me any more questions about that. And it turns out, again, stepping aside in the real world, and Josh may have run into this. I don't know anybody else who's maybe close enough to GCMs or mesoscale models to talk about what's called subgrid equations, where you actually start solving things at a resolution finer than the grid you're working on. And that has been the philosophic approach that some very large numerical models take. They actually stop at each grid point and consider in a separate manner a lot of details inside that grid, and then they go back to the grid level. Because if you try to actually mix the two, it gets so complicated nobody can follow it. I'll give you an example. The UK Meteorological Office has a Mars climate model run by Steve Lewis, I think. And when that thing is running full up, it cannot keep up with real time. On a modern computer, it cannot run as fast as actual time on Mars. It is that complicated.
Where, if you were to break this up and send out the tasks to separate cluster nodes, would you break it up at latitudes probably?
Probably, yeah. That would be a good start.
Or down?
Unless you're trying to do a seasonal, if you're trying to do the how much atmosphere is condensing out, the latitudes aren't really independent.
That's right. The only way they're connected is the polar mass. Other than that, they're separate, and you could divide them up.
I mean, if you're thinking of, like, so you could you do all the polar latitudes, figure out the polar mass, and then send that off to the other 35 nodes doing the other 35 latitudes and have them done in parallel?
Well, actually, about half the latitudes are polar. Mars polar caps come down to 45 degrees.
Oh, okay, but you could do the polar, I mean, so you...
But you could, there's no reason you couldn't run, you could parallelize this very cleanly in doing all the latitudes, and you wait until the last latitude finishes, adjudicate between them in polar mass if you wanted to do that, and then go on and do them all in parallel again. You could do it that way. However, the bottom line here is if you're not studying polar mass itself, you might as well use the Viking curves, because we know they're the actual answer. And the other one thing that's a side issue, science issue, even though Mars has quite a range in climate year to year, the pressure variation doesn't change very much. Is that still true, Josh? I think. Well, I don't, the Viking measurements were pretty accurate. I mean, it was a high precision gizmo compared to the modern ones. But anyway, the point is, you're going to want to do this pressure variation based on polar cap mass only if you're studying the polar caps. And very few people are doing that. So the answer is there's no reason you couldn't do it fully parallel on latitudes and running as many latitudes as you wish.
Even with the polar case separate, since you said that each latitude is treated individually, why the sort of...
Oh, it's the pressure. The thing is that those things that have to do with atmospheric opacity are based on the local surface pressure. And at times of the year, there's just more atmosphere than there is at other times of the year, and that depends upon the polar mass. And so if you're running this thing in the mode where pressure depends on the integrated polar mass, then they're coupled. That's the only case.
So if our season is 16 days, then we can extrapolate the converged solution in between each of the days in that interval and at each hour within each of those days as well.
That's not the way it works. Sorry.
No, I think you said after you're all done.
Yeah,
After you're all
you run.
done, you've run the model and you've got a set of temperatures for here and here. What is the temperature at this LCBS? You would interpolate between
That is
them.
correct. Is that the question you're asking? Yes, that is correct.
And similarly with time, you
Right.
interpolate between the 48 time steps or whatever you
Yeah.
store.
So what is there a certain season length where all those predictions are accurate? Like, does the accuracy change?
Yes, and numerically, I don't know. It's been, this is a question you should answer yourself.
Okay.
And the easy way to answer it is when we're done all this, you can see how to set the convergence parameters and the number of days per season. And this is I think the effective way, not necessarily the proper, the effective way to test how good is the model is you run it in different modes, some of which may be fairly expensive, not anymore, but in a sense expensive, and you compare the results. And it's adjusting the finesse, the fineness of the model until it looks like it's appropriate. And it's, with KRC now, this is a piece of cake to test because you can run all these cases. It takes you far longer to figure out how to set up the input file than it does to run the model.
All right, it's 10 to 12-ish. Well, I was going to say, when do people want to stop for lunch?
Can I get a question in?
Sure.
So you have the latitudes above the day.
Yes.
You only converge the curve for a single day on one specific latitude.
Yes, I converge. I do. It runs for a given latitude. It runs until it converges.
Okay. So, and you use that convergent curve for that particular latitude only, then you move ahead to a different latitude.
That's right.
Do
That's.
things over again.
I believe, I'll go back and check the code, but I believe that's correct. For a given latitude, it starts, it runs for a number of days, it reports back what it got on all days. The latitude program, TLATS, takes the last 3 days and it makes a prediction. And it keeps it, stores it as a function of latitude.
Okay. So different latitudes can converge at different rates.
Yes, yes, they can.
Okay.
In fact, that's very common.
Okay.
Somebody asked, Phil, you said you run 3 to 5 days. There is a parameter, which I think is called NR-set. There's a parameter which is the minimum days you run before you even look to see if we could be at last day. And I normally set that at 3 because if you're going to do, it doesn't make any sense if it's less than 3. But you could set that to be 6. You could set it to be 17, which is the number of, actually it's like 17.2 days. So if you set NR-set to be 17, you're guaranteed that it's going to run 17 out of 17.2 days and do a small prediction. And that, there's no shenanigans there at all. You just set that big because it doesn't even look. On the last day, there's a bunch more code at the bottom of the time step loop, but things it does on the last day.
Just a silly question, why is it 37 latitudes?
Pole to pole with 5-degree separation. And I used to run the pole, and there's no point in running the poles. I usually run about 88 degrees now as being close enough.
See, pressure compensation is independent of the latitude, or also independent of your individual runs. You're doing it for every single run separately.
Yes, if you turn on pressure, if you turn on the polar cap integration flag,
Yes.
then every run, every case, which is a case, a case is a set where all the conditions, the physical parameters are not changed. Okay, and then you run, and actually typically the way this thing runs is, I haven't talked about this yet, but seasons, normally I run for 4 years. And I don't record the first 3. That's what's, in the modeling world, that's called spin up. So I run for 3 years just to let all any kind of startup conditions get attenuated. And then I only record the last year.
So this is a really important point, and I'm not, okay, this is I think a crucial point, because we did this, okay, and we did this spin in place until you're linear and predict. Okay, and you go all the way around and you get to here, and I've got some temperature. And I use that to predict this guy.
That's correct.
And I do the whole thing again, and lo and behold, this thing I saved, the second time around is going to be slightly different.
Yep.
Okay?
And I actually do it.
So you really haven't stabilized. And so that's year 1. Oop, I'm a little different. Year 2, perhaps I'm a little different still. Year 3, okay. And then finally, year 4, now that's what you actually saved.
Okay. Now,
Right?
right. And the reason for this is this part up here, on this roughly the diurnal skin depth and somewhat more, is in fact virtually the same every year, because it's thin enough to be responsive enough to the seasons. It's this part down here, increasingly as you go increasingly deeper, it takes longer and longer to reach the proper solution.
And 3 years or 4 years, that's from Hugh-Kiefer experience?
Yes, if you have set the total number of layers to be about the annual skin depth or a little bit more. If you play Bob Haverly, oops, sorry, Bob. If you set the depth to be a millennium, it's going to take a millennium to converge. And so that's, again, the idea of scale height, skin depth, diurnal skin depth, annual skin depth. These are numbers you must understand and actually understand the quantities if you want to run something like this efficiently and hope to get the right answer.
So,
It's whatever you want. There are 2 numbers. There are actually 3 numbers. There's starting date, and I forget what it's called. DJ. Well, we'll just call it. There's start date. There is delta day. There's number of days, and there's a thing called J-disk. So you start at this date, you increment by this date this number of times. Typically, this will be something. This will be 1/40th of a year, for example. It helps to make it an integral of a year. This will be, let's say, 4 times 40. And this will be 3 times 40 plus 1. This is the day where it starts to record. And you can choose, see, it's the relationship between these 2. When do you start? When do you stop recording? And you can make those sometimes I intentionally run here's a trick. You should all be aware of this. Make this not 3 times 40 plus 1, but 3 times 40, so that you record one season twice, at the beginning and the end of your run. Because that way you're going to get this guy, you're going to get once, and you're going to get it at the very end. And then you can look and compare the two and say, what changed? Have I converged or not?
But that was going to be my question, is there a way in KRC, let's say we start fiddling around with layers, and is there a way to say, I want to look at season 1, 2, 3, 4, and do exactly what you just said, and say, hold on, fella, you're not converging yet.
Well, yeah, you can output, as long as this number is 1 or more, that's when it starts. If JDisk is 0, it never creates an output binary file.
Okay.
And that's in fact something that Ken and I got into the other day. I was running something and I forgot that this was 0, and so I was looking for a file that didn't exist. But when another philosophy statement, when you're doing numerical modeling and it's a relatively new field to you or a new model, test the bejesus out of it. Try, test all your convergence parameters. Run things with fine steps, with coarse steps. Look and think about the answers.
KRC gives you lots of rope in which to hang yourself. That's the short of it, but you have the flexibility to test all these different things to make sure that the results make sense.
Yeah, there's hardly any constants in KRC inside. Pi may be the only one, and I think we know that pretty well.
E's in there.
E's probably in there someplace, but that's, it was intentional to move all this stuff out to where it was accessible.
So, sorry to repeat my question.
Okay,
once
sorry.
Again. Same thing about when you enable the variation of pressure due to the polar cap buildup.
Yes.
How would you change those diagrams that fill through those curves?
And this is something I've actually tested. If the conditions at a given latitude are such that the polar cap disappears entirely during the summer, then all this discussion is okay. You should approach convergence at a given season. The conditions should be the same year to year to year, because you're actually repeating. If you set things so that once the polar cap grows, and there's instability, there's there's positive feedback in polar cap systems. That's the reason why the Earth is in so much trouble at the moment. There's positive feedback in that when a polar cap forms, it typically raises the albedo, lowers the amount of absorbed sunlight, and lowers the average temperature, making polar caps even more stable. That's negative feedback. That's positive feedback. And in which case, the temperature profiles will begin to converge, but the mass of the polar cap will continue to grow just forever. And so one of the parameters KRC puts out in some file formats is how much CO2 is there at every latitude at every season. And you want to check to make sure that, if it's of interest to you, that you don't have a condition where you've got a runaway polar cap. But other than that, apart from a polar cap lasting through the summer, and that is never completely going away, things should converge whether or not there's a polar cap. But another word, in case I don't mention it later, using in a system that has positive feedback, And that is, it can have two stable states. In this case, it can have dry soil or growing forever polar cap or seasonal polar caps. Be very leery of what happens at the edge of that boundary, at the edge of the polar cap. It's not, and that's a problem with the current production model. It interpolates between different models, and when it does it near the edge of the polar cap, you may get a pretty wild answer because you're interpolating between two things which are bistable, and they can diverge. So any numerical system at the end of a positive feedback boundary is going to be questionable. Is that okay?
All right, Mike.
Sorry if you already said this, I just want to make sure that I got the answer right. The latitudes are all independent. There's no
That is correct.
crosstalk between them within the case.
That's true in all aspects but one. And that one is in a subroutine called TINT, T integrate. And that's the one that integrates the polar mass. And it, in order to calculate the area assigned to each latitude, because it takes each latitude and assumes that the area halfway to the next latitude in both directions that is represented by that latitude, that requires that they be ordered from south to north. That routine is not clever enough to look for disordered latitudes. And that's the only case in which they're coupled. So if you're running polar sets, if you're going to, and the other thing is it makes the interpolate, Kim would shoot you because she has to interpolate all this production code stuff, assumes that things are nicely ordered. But in fact, in KRC itself, the only place in which the order of latitudes is important is in polar cap mass integration.
So typically, if you're running a KRC run, you might only actually specify, I want to know the temperature at 35 degrees north. Now, if I did that, what does KRC do? And I said, I'm not going to care, I'm going to use the Viking pressure, and I just want the temperatures at 35 north. Does it calculate any latitude other than 35?
Nope. Doesn't even look. In fact, the way it's written, there's a parameter that says how far into this storage area that represents latitudes and elevations, how far do I look? Because it's Fortran again, I got to allow room for 37 or some other number. But one of the input parameters tells it how far do I look, and it doesn't care what's after that. It never sees it. It may even be printed out. You could be misled because you can print it out, but Cache doesn't care. Just, I gave it 103 and it prints out 103 and I never looked. Okay?
Okay, so I'm going to reiterate, I think this is probably a good place to pause. Okay, so I don't live on this side of campus, so I don't know what the lunch options are.
But the .bin5 files, which are used for 5 of the 8 output modes that this thing has, are dynamically dimensioned. It's done in Fortran by calling primitive C routines, which allow you to do absolute addressing. I did not write those C routines. Actually, Chris Becker at Flagstaff wrote them. They are part of the system. They're very primitive, and they So they should be almost rock solid. I don't know if Dale is
They're
in.
Alex and Alex and free, yes.
Pardon?
They're Malix and Alex and free. It just frees memory, just like
Okay.
C would.
Okay.
That's all it is.
It's not Fortran friendly, so there's a lot of convoluted Fortran in order to actually do this. Because I actually construct the array in Fortran and then hand it to something that can write a variable sized files. And I don't know, I just stuck this in here for those of you who are not familiar with thermal inertia. It's just a slide showing thermal inertia calculations by KRC. This is one that's got 24 hours in a day, so it's a little bit jerky around the dawn and dusk. And it's a typical thing of what happens is the inertia gets lighter, smaller, and eventually you approach equilibrium with sunlight. And this is the time of day that Themis, where is it now? It's almost
Moving back.
moving back.
It's about 4 p.m.
Okay. Well, anyway, this is just a slide. Here's another. Has nothing to do really directly with KRC. It's the relationship between thermal inertia and particle size with the conventional Wentworth scale. This is stuff you guys would be familiar with. And how we handle frost and snow. I believe I've covered all of these except that one. Supercoolants. The atmosphere starts to fall below temperature. I've basically said this. It adds energy by allowing CO2 to condense. So it just sucks energy out of the CO2 condensation process. That keeps the atmosphere warm. Throw the snow on the ground. We've mentioned this one. This is a peculiarity of Mars. The albedo increases with solar intensity. All of that we've covered. So we're doing great. 2 slides in a minute or something. This is a good question. How close is KRC to Mars? And it's based on, in a sense, I mean, best estimates are changeable all the time. Everybody's responsible for their own input parameters. But the ones that are there are defaults, and they're close to Mars. I've said this, absence of wind effect is probably the largest shortfall. And beware around the edge of a seasonal cap. This is that generic, beware of working near the edge of any positive feedback process.
I could complain about KRC a little bit here, like where the shortcoming is. I always felt one of the biggest shortcomings is maybe semi-related to wind effect, but not entirely, is the dynamic atmosphere. And for example, you have Hadley circulation, which brings a whole lot of energy up into the north at certain seasons. And that, I've seen that have massive, very big effects on things. So that would be, if I was going to say there's a shortfall, that would be one of the major.
But we're not a GCM. Yeah, I know.
Yeah,
It just isn't there.
exactly. And not that I'm expecting it to be there. It's one of those beware type things.
Yeah, no. If you really want to, a person in your situation that was concerned about that would have to find somebody with a GCM to work with. And this whole business of comparing models actually is not that trivial, of trying to see, what are the differences and then understand why are they different. I don't have any answer to that. KRC is a one point at a time model the way it's currently structured. Okay, this is the beginning of the input file discussion. Everything basically is controlled. These are the numbers. How many layers, how many hours a day, how many latitudes, how many seasons, which latitudes, which seasons, so forth. And the seasons all come out of this start date delta season, the first date to disk, and the number. And how many seasons. Those 3 plus how many seasons are the ones that are over here on the wall. This one, index of major changes, is something that probably none of you have used. there's a variable that's innocuous, but at a certain season you can get code KRC to go back and read more input without restarting. It's a somewhat hazardous thing, and I haven't described it very well, and I've almost never used it, but it's actually in there. We've talked about two materials. You can have either both, but not one. Has to be temperature dependent. If you want to have only one temperature dependent, you simply put in zeros for the first, second, and third order coefficients. It's a very easy way. KRC will run as if all or neither are temperature dependent. But you can make the temperature dependence as small as you wish, even 0, by putting in numbers with only the constant term in the first, second, third order dependence, and temperature is 0, and there you go, you get temperature independence. I have run tests with KRC where I put in 0 temperature dependent coefficients and then run it with and without the temperature dependence turned on, and the differences are in the millikelvin range. It's actually executing very different code, but it seems to do it right. There's a whole bunch of the atmospheric properties I've already mentioned, including the scattering parameters. This insulation-dependent albedo is an option. The thing about how much frost it takes to continuously change the albedo as the frost thins, those are all input parameters. Planet orientation, all this is stuff. Layer and time scheme. The convergence criteria are input parameters. I would say it's not a novice thing to modify those. It could be done, but just have to start being thoughtful about it. The print output, this is a sleeper. Remember, KRC was generated when there was no such thing as a binary file output, realistically. It was just paper. And you can turn on flags that will generate voluminous, and that's an understatement, output. I mean, it's easy to get megabytes of print files. And so and they're very handy for some things, but you just want to be thoughtful about it. And you may want to limit the print file size. If somebody turned all the switches on saying, well, I'll see what it do, and they ran a full case per year, you're going to swamp the system. And we talked about output files. There's 3 versions of Fortran sequential access and 5 versions of bin5 files. And I'm saying most users will be fine with type 52. It's probably only one you need to worry about. It'll be a little more voluminous than you need, but it's got almost everything in it. The problem is it's Fortran. Well, you need a reader for type. We'll get to type 52. They're doubly packed files. I thought this was interesting. I realized this is an understatement. KRC isn't a tool, it's a tool shed. It's full of tools. You can turn on and turn off all kinds of things. It was originally designed for the sets of uniform global models. That was the original incentive. And it's been used that way a great deal. Viking used 3, Themis used hundreds. In the paper, there's a global average temperature map. I used nearly 1,000 models in that. It actually took, more than an hour to compute this stuff. You can look at studies of focus, models of rock proportion. You can do all this kind of stuff. This is something that you probably haven't encountered. KRC can go through this process of going round and round to get the deep temperature profiles established. And then if you want to, you can set it to do every sol and put out information every day. So you can spin up for years quickly and then go into horrendous detail. I don't know of any other model system that allows you to do that. But I put it in partly because I was interested in what happens in the spring in the polar caps. You got to develop this cold subsurface based on accumulating solid CO2, and then it goes away. And then what happens to the temperature? Well, it turns out it changes really rapidly, of course. The last bit of snow is gone, what we colloquially call the crocus date, and KRC can handle that for you. There's the 1-point mode. We'll come back. Phil ran 1.5 billion points so it's well exercised at least. I don't know if it's right, but it's well exercised. This is important. There's a help list which you have, and as we start getting into details later in the afternoon, we'll probably go back and forth that. The website, I'm going to hope we only have one maintained version, and ASU will be responsible for version control and whatever. We'll see later at the almost last slide, I actually started to think about how to put a version number in that gets into all the different forms of output. And we'll have this distribution, which is people are already working on. It's got all the source code, sample files, documentation, sample output files, so you can test whether or not your output seems to be working right. And so the question is, this is the big question, what do you want? You, the user, the back row users. You just decide what you want. And I would guess in the future, if we filled in the rest of the row with people who aren't familiar with KRC, they're going to talk to the mentor, to figure out how to get what they want. This is like, I think that's why you need live help, amongst other reasons. And so this is the normal output. Surface kinetic, planetary, and atmosphere temperatures every hour. The minimum and maximum diurnal temperatures for each layer, that's there. For each latitude, this is what's in type 52. It has all this stuff. How many days to converge, the RMS temperature change on the last day for every layer, predicted atmosphere temperatures, amount of frost, the frost albedo, the mean upward heat flow into the surface. All those are there. And then there's stuff about the actual Julian date, LCBS, atmospheric pressure at 0 elevation, dust opacity, total frost. These are all global values. And I've written IDL readers for every output format. I'm probably going to recommend type 52 to start with. We'll have to decide how many different output readers you wish to maintain. There's a DaVinci interface to this. I think it's to a prior KRC. I don't know exactly what version it is. Somebody just needs to check it and test it.
That's on the list of to-dos. So.
Yeah.
Now, when you ask what you want to do, is that a rhetorical question, or is
Yes. Well, it's not rhetorical. No, it is. You decide what you want to do. I mean, that's I suppose one of the advantages of KRC is it has a great many different modes it can be run in, including this business of sort of changing modes in the middle. And so there's a large number of flags and constants and things. You have to decide what you want to do. And if people were doing a big mapping job, then the first thing you do is figure out, roughly how am I going to set the parameters, and then what cases do I want to run. And so you got to decide what you want to do. The input file, I'll go over this quickly. The way to go over it thoroughly is to read the help list, because every parameter is described there. Here we have in red, here and here, that's L, K of logical, K of temperature. If this is set false, then these values are ignored. Otherwise, you need to put in 4 terms that represent the cubic form of the conductivity of the surface layer scaled to a scaled variable, T minus 220 divided by 100. That's the scale temperature, which is a number that basically goes from -1 to +1, which makes the cubic evaluation less prone to round-off error. It's just a standard numerical trick to minimize round-off error. So those 4 numbers represent the conductivity of the upper layer, and then there's the conductivity of the lower layer, and then the specific heat of the upper layer, and the specific heat of the lower layer. And they have to be there. This is a little strangeness. I think that I forget whether this is list directed or strictly formatted. I always try to keep everything aligned. You'll see, this is my habit, is to keep everything aligned, which is not so important if there's a decimal point in the field. It's critical if there's not a decimal point in the field. That's the way Fortran works. If it doesn't have a decimal point, it presumes the decimal point is where you said it is in the format statement in the code. But ones with the decimal point in a floating point field can be anywhere as long as it's there. And so all these parameters, these are all the floating point constants, the temperature dependent section, 2 lines, no, 2.5 lines, 20 integer items, and 16 logical items. The ones people commonly change are things like albedo, thermal inertia, starting date, delta season. Down here is the number of seasons altogether and the first season you're going to output. Here we have the number of layers, the number of time steps in a day, the number of days maximum to convergence, the number of latitudes, the number of seasons. And in common, these are J1 through J5 in common. That's the actual value of the index. Number of output times per day. Yes? Question?
So getting back to my comment earlier, I could blithely go through and change f-lay from 0.18 to 0.018 and change N1 from 20 to 200. What would happen?
It would gag because the coded maximum for N1 is 30 at the moment.
Okay.
That's what would happen. It would probably set it to 30 and perhaps give you a warning. Then it should run just fine, I think. When we get to the convergence table, the first thing you do is run it and look at the convergence stability table. Okay?
I'm not trying to beat on this layer thing, but I do think what we've learned about Mars in the last 10 years, I agree with what Josh said completely about atmospheres, but interestingly layered sedimentary regolith on the surface of Mars is crying for fine-scale layering.
What I would suggest you do is look at the convergent stability equation, the criterion, think about it, and decide, okay, how far do I need to push KRC in order to obtain the vertical finesse that I want? And then decide, okay, do I use this or I go to Crank-Nicholson or some other unconditionally stable routine?
I would much rather work with you and get
KRC to do what I wanted to do than have to go and learn some new,
I understand.
black box.
Well, that's fine, but nonetheless, you're going to have to do the work to figure out what the stability regime is.
Understood.
If you want to go smaller than this by a factor of 1,000, your time steps are going to go up by a factor of 1,000,000, which may not be important with all the computing resources you have.
Yeah, I mean, to me, it's easier to just let the computer run for a longer time and rewrite them.
Yeah, but there are other things there too, and you might have to go to double precision, because even though the problem doesn't require double precision, you remember those lunches we had? We used to have discussion lunches at UCLA, and I would take the petition.
I mean, the Da Vinci front-end for it kind of does something like that.
Yeah.
There's,
It manually constructs this file based on just input with command line on Da Vinci.
I mean, my sense in working with students over a long period of time is this is profound, but it's also a barrier in the sense of just, not the content, but just the mechanics of having, like for example, I got into a lot of trouble and I needed Randy to help me when I was trying to do that model, that movie. the way it was set up, I couldn't get enough decimal points in the local time such that I wasn't seeing little grids in my movie. I wanted to run it every 5 minutes or something. And so just little things like that are
Right. Well, okay.
Can we fix the input such as a nice, simple, user-friendly interface that constructs this table?
Because what you were just talking about is that was the 1 point file, right?
Maybe, yeah, I don't, it's been a long time. But
That's probably the one. I think you use one. Well, let me say let me just try to present a concept here. There are two classes of solutions to this problem. One class treats this as the input file to KRC, and you can put all kinds of stuff in front of it to generate this. You can have as many versions of that as you want. In fact, Tim Titus has a big IDL routine that does that for making loops and things automatically. And then the other class of solution is where you actually change the input that KRC reads itself. And that's also possible. What I've thought of is I would love to see a modern GUI interface here which had words and blanks and maybe even descriptions and warnings, and you can click on something and it goes HTML to description and says beware, a real hierarchy of input where you can go back and forth, up and down without having to read the help list.
or install DaVinci. And so